Section 9.3, center of gravity. Definition of center of gravity is the center of gravity of a rigid body is the point at which its weight can be considered to act when torque due to the weight is being calculated. Center of gravity, it turns out, is basically identical to our center of mass, what we saw before as the balance point. What we're saying is that for this ruler, for instance, all of the weight of the ruler in terms of torque can be acting at this point right in the middle till you tip it off, right? This allows us to calculate the torque that an object like a ruler can cause. We're now considering how if you grab just the end of the pencil, that's not enough to support it because it's going to create this torque that will cause it to rotate as it falls. Now, how do we know where the center of gravity is? Well, if an object has a symmetrical shape and its weight is distributed uniformly, the center of gravity will lie at the geometric center. If we go back to the ruler that I had, because it's pretty uniform, the center should be right in the middle, about 6 inches, right? So if we check that out, that's pretty good, right? So this is a very convenient thing. Anytime a problem mentions that a shape is uniform, like you have a uniform board or a uniform plank, that tells you where the center of gravity is located. That tells you that the weight acts right in the very middle of the length. And that's what's depicted here in the picture, that for this, whatever flap this is, maybe it's a door, maybe it is a shutter that opens up, the center of gravity, if it is uniform, will be half of the entire length. And so you can say that the force of the weight acts at that point, which is going to be half the length away from the axis of rotation, and that will help in calculating torques. So this alone is a really great principle. There are some instances where you want to calculate the center of gravity for a more complicated set of shapes. So maybe you want to calculate the center of gravity for not just the stick, but the stick when I also have a block on one end, right? When I add a block to one end, now the balance point is not in the middle. This is not going to balance. Well, where is the balance point? To find that, we can use this equation, which you'll notice looks very similar to our center of mass equation. This is xcg for the center of gravity. It's equal to the weight of one object times its distance, x1. This is different from the lever arm. It's just the distance from our access point, our reference point, plus weight 2 times its distance to some reference point, such as the axis. And you can add up all the weights and times their distances and divide by the total weight. That will give you the center of gravity relative to that same reference point. And at that point, it should all balance out. This, I don't know if it will actually balance. But we can do the calculation, actually. We're not going to do that here. But if you're interested, it's something that can be calculated. There was some balance. All right, so let's see an example of this, the center of gravity of an arm. So the horizontal arm could be considered to be composed of 3 parts, the upper arm, the lower arm, and the hand. And each of them has their own weights. So where does the overall weight of the arm act? That's something we can figure out. So we'll figure it out relative to the shoulder joint, just as we did with the deltoid muscle example. And we'll use the information given here to find the center of gravity relative to the shoulder joint, and they give the distances to the middle of the upper arm, the lower arm, and the hand, right? Distance to the middle of the upper, distance to the middle of the lower arm, distance to the middle of the hand, because we know that the middle of each of these, if we assume, which it probably says that we should have assumed, if we assume that the upper arm is a uniform distribution of mass, then it would be right in the middle where its center of gravity is. That's about what they depict here. If not, we can just assume that they're putting it where the center of gravity is acting. So we know these distances, and we know these weights, we can find the center of gravity of our arm. We're just going to go to that equation we just saw and plug and chug away. So put in the weights, such as weight 1 times its distance. The upper arm has the largest weight because it's the most massive, but the smallest distance. The lower arm has a smaller weight, but a greater distance. The hand has the least amount of weight, very lightweight, but it is the furthest out, so it contributes a fair amount in that regard. And then divide by the total weight, and we find the center of gravity is 0.28 meters. So let's check where that is. 0.28 meters, that would be somewhere around this elbow, right? It's somewhere filling in here, maybe a little into the lower arm, maybe not. I'm not, yeah, if this one happens to be in the middle, then 0.13, this would come out to 0.26, so it'd be just dipping into the lower arm a bit. Pretty close to the elbow, which is a convenient measure. And it's fairly close to the halfway point of this 0.61, right? Halfway would be 0.305. It's just slightly shifted towards the upper arm because the upper arm has so much more mass. Right, let's also look at a conceptual example, overloading a cargo plane. This accident occurred, this is a real photo, because the plane was overloaded toward the rear. How did a shift in the center of gravity of the plane cause the accident? So we want to come up with an explanation for what's going on here. Note, this is not how planes are supposed to be. We see another plane at the airport and it's very nicely sitting up at the gate. This one has its wheel up in the air. That's a problem. The wheel is not meant to be there. So what's going on? Well, we can think about the wheels of the plane, right? There's some other wheels back here, somewhere in there. And what kind of force do those wheels supply or feel from the ground? Well, that's where they get support from the ground, pushing back up to support the plane. So what happens when too much of the weight shifts back? Well, in that case, this front wheel isn't able to support very much anymore. All right, let's look at a schematic of this. So with normal loading, you keep the center of gravity of the plane close to the middle or even slightly forward on the plane. That's between the two wheels, these two support points. And that is very stable. If you have the two support points, you want to add in a load in the middle and it won't tip. If you instead add a load to the rear, it's gonna tip things, right? Because now the support points aren't able to hold the plane down. And that's what happened. Apparently they started loading up the rear of the plane before loading the front. So that shifted the center of gravity of the entire plane back enough that the entire plane tipped. It was off kilter. So the center of gravity does have some important implications for stability of airplanes, but also if you have a car that has an extension beyond the back wheels, you want to be careful how you load that. You don't want to cause your car to tip by putting too much in the back. And we showed an equation for calculating center of gravity. You can also get it with an irregular shape by this experimental method, which is actually pretty nifty. So if you have a strange shape, I don't think I have any good strange shapes right now, but assuming you had a strange shape, you can hang it by any point of that shape. And because of the center of gravity's pull, as long as you haven't hung it directly under it, that's going to create a torque that will make it rotate until the center of gravity is directly below the support point. At that point, there's no torque on it. It's not going to rotate anymore. So this strange squash-like shape, right? It rotates until it's vertical, and now the center of gravity is right below the support point, so there's no torque. and you could draw a dotted line on this vertical line, and you know that the center of gravity must be somewhere on this line. If you repeat this process, you could hang it from a different point. Again, the center of gravity is going to cause it to rotate until it comes to a balance point. Then you can draw that vertical line because you know the center of gravity is somewhere on that point. And where those two lines that you've drawn intersect is the center of gravity of your object. So that's a pretty nifty way. The other experimental way, as I've mentioned before, is you can actually find the balance point, right? You can find the point where there isn't a net torque on either side. And that is where the center of gravity is acting for that object. All right, this introduces the idea of center of gravity, which again, is really just an expansion of our understanding of center of mass.